Assalamu alaikum. Today's lecture will talk about the hydroelectric energy resources. During this lecture, we'll talk about the hydroelectric energy generation. We'll go through introduction to hydropower, hydraulic turbines, Pelton turbine, Francis turbine, Kaplan turbines. We'll see what is the definition of draft tube, and we'll talk about the unit quantities, specific speed, and the characteristics curves of hydraulic turbine, and we'll finalize with the hydraulic power systems. This is the introduction to hydropower. So what is the definition of hydropower? What is the meaning of hydropower? Hydroelectric power, often called hydropower, uses the energy in falling water converted into electricity without using up the water. So it is considered as one of the renewable energy resources. This is the second most common form of renewable energy in the world. Most efficient energy source. Efficiency can reach up to 90%. Hydroelectric power generates 19% of the world's energy. And you can see here, this is the reservoir, this is a dam, and this is the tunnel that the water go through it, intake, and this water will go through the turbine connected to the generator, and this is the outflow after the turbine. And in the other picture, you are going to see the same components of the hydroelectric power. Consists of reservoir, this called penstock, and at the end of the penstock, the turbine is installed, connected to the generator and power plant. This another view shows the generator connected to the turbine, and this is the flow of water. It flows in this direction. It's going to rotate the turbine and generator and generates electricity. Hydroelectric or hydrologic water cycle, we can say that the hydropower energy, its indirect solar energy, is ultimately derived from the sun, which derives the water cycle. In the water cycle, rivers are recharged in a continuous cycle. Because of the gravity force, water flows from high to low points. Here is the water cycle, and you can see that when the sun comes, it will evaporate the water from the lakes, rivers, seas, and there is a condensation, transport, precipitation, snow melt, run off, and goes back to the surface, run off, and some of water goes infiltration into groundwater flow, plant and uptake, and so on. So this is a water cycle, and during this water cycle comes the hydropower generation or hydropower energy. Here we'll talk about the types of energy. We talked about the types of energies. One of them is called potential energy, and the other one is kinetic energy. So first of all, potential energy is the energy stored up to do work based on its position, like water behind the dam or a ball on the top of a hill. So in this picture, it shows the water behind the dam in the reservoir with a high head, and the water is going to flow through the penstock. So the water behind the dam, it has potential energy. Once it moves through the penstock, so the potential energy will convert to kinetic energy. So kinetic energy is the energy of motion. Any moving object has kinetic energy. This kinetic energy will hit the turbine and will try to move the turbine to generate electricity. So the mechanical energy is a form of kinetic energy, such as in a machine. So mechanical energy has the ability to do work. This is what's happening in the turbine or in hydroelectric power turbine. Water wheel. Water wheels, humans first learned to harness the kinetic energy in water by using water wheel. So the first form of using the water energy or the flow of water energy is in the water wheels. So the water wheel is a revolving wheel fitted with blades, pockets, or veins. Water wheels convert the kinetic energy of flowing water into mechanical energy. So the main purpose of water wheel is to convert the kinetic energy of flowing water into mechanical energy that will rotate this machine. Water wheels in history. Actually, the early water wheels used mechanical energy to grind grains and to drive machinery such as sawmills and blacksmith equipment. In early days, the water wheel has been used in different uses, like to grind grains or to drive machinery like blacksmiths and sawmills equipment. This is one of the ancient water wheel that is going to use for grinding grains, for example. The first hydroelectric power station actually done by Edison. So Edison has invented the first hydroelectric power station, and it was constructed in 1882 in United States. It produced 12.5 kilowatts of electricity, which was used to light 2 paper mills and 1 home. Hydropower turbines worldwide. There are many different forms of hydropower that are going to use in all over the world, and all of them needs dams to reserve water and penstock to generate or the water flow to convert the water flow energy into the mechanical energy to rotate the turbine and then generate electricity. Hydroelectric turbine and generator. This is the picture showed the runner of the small water turbine. This is the runner of the turbine, and here this turbine is connected to the generator, as we mentioned. So the top section or the top part is the generator, consists of rotor and stator, and the turbine itself connected to the generator through the shaft. And the turbine consists of blades, like here you see blades, and wicket gate or wicket gate, and the water flows in this direction that will hit the plates and then will rotate the plates of turbine and then will rotate the generator and generate electricity. One of the main popular types of turbines called Francis turbine. This is a picture. This picture shows the Francis turbine example at Grand Coulee Dam in the United States. This French turbine runner rated 1 million horsepower. 1 million horsepower or 750 megawatts of electricity. You see, it's a huge turbine. And this picture showed the Grand Gully Dam, and this hydropower turbine connected to it. Another type of hydroelectric turbine runner, it's called propeller type. Propeller type runner rated at 28,000 horsepower, or it generates 21 megawatt of electricity. And actually, you see the runner is too big, is much bigger compared to the human being. So if we look into the various types of water turbine runners, we'll see different types like Pelton wheel. This is called Pelton wheel. These two types of French turbine, this is French's, and also this is another type of French's turbine, but one for low speed and one for higher speed. And the third type of turbine called Kaplan turbine. This is Kaplan, how it looks like. Here in this chart, it shows the water turbine application chart. Here, where you can see the horizontal axis shows the flow of water, flow rate, and the vertical axis shows the head, the height of the water behind the dam. And you can see Pelton, for example, Pelton turbine, the red one here, it works at high head with low flow rate. French's, the yellow one, it can cover all types of water flow rate, but it works for higher head. The third type, which is the blue Kaplan, the Kaplan can work at lower head, and it can cover the different types of water flow rate. So according to your application, you can choose the type of turbine. Also here, in terms of the electricity needed, so if it is needed to generate 1 megawatt of electricity, so you can use either Pelton here, French's here, or Kaplan here across this straight line. If you are going to increase the electricity amount of electricity generated, so you are going to work on different line, then you are going to see what type of turbine that will achieve this. Here, the typical range of heads for different types of turbine, we can see that the water wheel, this is the simplest form of water turbine. It can work at a small head in meter from 0.2 to 4. Very low head turbine from 1.5 to 4.5 meter. Screw turbine up to 10 meter. Kaplan turbine up to 70 meter. French's turbine up to 300 meter. Turbo turbine up to 252 meter, and Pelton one up to 1,600 meters. So according to the head needed for your hydropower turbine, you can choose the best turbine type. This is another type of water turbine. It's called screw turbine. Screw, it's used as a small hydropower plant. This is one example of the screw turbine. It generates 12 kilowatt at a small hydropower plant in Poland. Now we'll talk about the hydraulic turbine. We mentioned that there are different types of water turbines: French's, Pelton, Kaplan, propeller, turbo, cross flow. These are the main types. We can classify the turbines into different classifications according to different things. First of all, we are going to classify the turbines according to the type of energy at inlet. So the inlet, what is the inlet? The inlet, this is where the inlet where the water comes inside and hits the turbine. This is called inlet. We're going to show you it later on, but here you have two different types of turbines according to the type of energy at inlet. We have impulse turbine. Impulse turbines requires high head and low flow rate, such as Pelton wheel. And there is another type called reaction turbine. Reaction requires low head at high rate of flow, like Francis and Kaplan turbines. We can classify also turbines in terms of direction of flow through the runner. If the direction of water flow through the runner tangential, this will be like Pelton wheel. If it is radial, so this is like Francis turbine. Or if it is axial, so this is like Kaplan turbine. If it is mixed, like both radial and axial, so this like modern Francis. So now we can classify the turbine as reaction turbine or impulse turbine. Reaction like Francis and Kaplan propeller. Impulse, the only type of impulse turbine is Pelton turbine. Here is in this, actually this animation, it shows you what the difference between impulse and reaction turbine. Here is the inlet, as we mentioned. This is the penstock and nozzle, and this is the inlet here, where the water comes out from this pipe and will hit the plates or the pockets or the vanes or whatever. So when it pushes in impulse form, so this becomes impulse type of turbine, like Pelton. But see here, in the other type, which is called reaction, the water is flowing in continuous flow, like Kaplan and Francis here. So if at the inlet of the turbine the energy available is only kinetic energy, the turbine is known as impulse turbine. As the water flows over the vanes, the pressure is atmospheric from inlet to outlet of the turbine. If at the inlet of the turbine the water possesses kinetic energy as well as pressure energy, the turbine is known as the reaction turbine. As the water flows through the runner, the water is under pressure, and the pressure energy goes on changing into kinetic energy. The runner is completely enclosed in an airtight casing, and the runner and casing is completely full of water. And these are the main difference between impulse and reaction. Reaction turbine, the turbine itself is totally full of water. So there is the water, it has pressure and also kinetic energy. But here the water is coming from this side and it only makes kinetic energy. Only kinetic energy is available. So this is impulse turbine like Pelton. This is a Kaplan and Francis turbines. The classification in terms of the direction of flow, we mentioned that there are 4 different types: tangential like Pelton, radial old Francis, it was radial flow, axial flow like Kaplan, and mixed flow like modern Francis. We see here what's the difference between these four types, tangential versus radial flow. Here in Pelton wheel, the water is coming in this way, so the water flow is tangential to the turbine or the runner plate. But in the radial flow in the old Francis, the water coming from the center and then it will move radially. So this is considered one of the radial flow turbines. In Kaplan, you can see the water is flowing in this direction and it will try to move the turbine in this direction. So the water flow is in axial direction of the turbine. So it's very clear the difference between the tangential flow, the radial flow, and axial flow. The modern Francis turbine actually it uses mixed types of water flow like tangential and radial, or axial and radial water flow. So here, if the water flows along the tangent of the runner, the turbine is known as the tangential flow turbine. If the water flows in the radial direction through the runner, the turbine is known as the radial flow turbine. If the water flows from the outward to inward radially, the turbine is known as inward radial flow turbine. And if the water flows from the inward to outward, the turbine is known as the outward radial flow turbine. If the water flows through the runner along the direction parallel to the axis of rotation of the runner, so the turbine is called axial flow turbine. If the water flows through the runner in the radial direction but leaves in the direction parallel to the axis of rotation of the runner, the turbine is called mixed flow turbine. So we are continuing in classifying the turbines in terms of the head at inlet of the turbine. For high head turbine types are called Pelton wheel. For medium head, you are going to use Francis turbine. For low head, you are going to use Kaplan turbine. Another classification of turbines according to the specific speed of turbine. Specific speed. Pelton wheel are considered low specific speed turbines. Francis turbine are considered medium specific speed turbine, and Kaplan one considered as high specific speed turbines. So when we put them in this graph, we can see the low head turbine here, like Kaplan, it works with less than 30 meters and it needs large quantity of water. For medium head turbines like Francis, it works from 30 meters to 150 meters and it needs moderate quantity of water required. For high head turbine like Pelton wheel, it works from 150 meters to 2000 meters and it needs small quantity of water required. This is in terms of head. In terms of specific speed, as we mentioned before, high speed like Kaplan work at more than 250 RPM. For medium specific speed like Francis, it works from 50 to 250 RPM. And finally, the low speed specific speed turbine like Pelton, it works at speed of less than 50 RPM. This table summarizes the classification of the turbine or types of turbines in terms of their specific speed. So Pelton, inside Pelton itself, there are different types of runner: slow one, normal one, fast one, with different specific speeds. Inside Francis also there is a slow one normal, one fast one with the different specific speeds. But for Kaplan, it works as a high, it works at a high specific speed. It has only one type. So the last classification of turbine according to the disposition of turbine shaft. This position of turbine shaft in Pelton wheel, the turbine shaft is horizontal, like here, it's horizontal. But in Kaplan and Francis, both the turbine shaft is vertical. Now we'll talk about some definitions and some basic definitions for hydropower turbine. Head of a turbine. What is the head? Actually, this is the layout of a hydroelectric power plant. It shows the water reservoir, dam, penstock, nozzle, turbine, vanes, and the water behind the dam has a height called gross head, HG, and the water after the dam just below the turbine, it's called tail race. Here is the head race with the height HG, and this is the tail race. So what is the definition of gross head? Gross head HG is the difference between the head race level and the tail race level when no water is flowing. Okay, clear? There is two different definitions, more definitions for head. One is the net head and the other one is HF, the losses. So the net or effective head, H. What is the definition of the net or effective head, H? The head available at the inlet of the turbine when the water is flowing from the head race to the turbine, a loss of head, HF. This is a loss of head due to the friction between the water and the penstock occurs. So H becomes HG, which is the gross head, minus HF, the head loss. This is the net or effective head, H. Now the question is how to calculate the head loss, HF. HF can be calculated from this formula, 4 times F times L V squared over D times 2G. What is V? The velocity of the flow in penstock. What is D? D is the diameter of the penstock. What is L? The length of the penstock. What is F? The friction factor. So once you know the F, L, V, D and the gravity acceleration of the gravity, G is a constant, you can calculate HF. Once you know HF and you know HG, you can find the net head H. Now we'll talk about the efficiencies of a turbine. The following are the important efficiencies of any hydroelectric power turbine. The first one is called hydraulic efficiency, eta H. The first type of efficiencies is called hydraulic efficiency. The second one is mechanical efficiency, eta M. The third one is volumetric efficiency, eta V. And the overall efficiency, eta naught. So now the question is, what is the hydraulic efficiency? Hydraulic efficiency, it is defined as the ratio of power given by water to the runner of a turbine to the power supplied by the water at the inlet of the turbine. So the hydraulic efficiency, the power delivered to turbine runner divided by the power supplied at the inlet. So the power delivered to the runner, we'll call it RP, and the power supplied at the inlet, we'll call it WP. That means the hydraulic efficiency is the runner power over the water power. If the runner power equals the water power, that means the efficiency of the hydraulic efficiency becomes 100%. Now, how to calculate the RP or the runner power? RP, the power delivered to the runner or the runner power, for Pelton has an expression, for radial flow turbine has another expression. For example, for Pelton turbine, it's W over G, VW1 plus or minus VW2 times U over 1000 in kilowatts. So what is W? The weight of water striking the vanes of the turbine per second. And it can be found from rho G cross Q. What is rho? The water density. What is G? Is the gravitational acceleration. And what's Q? Q is the volume of water per second. Once you know rho G cross Q, you can find W. What is VW1? Is the velocity of whirl at inlet. What is the velocity? What is VW2? The velocity of whirl at outlet. What is U? Tangential velocity of vane. When the water hits the vane, it will rotate with the tangential velocity U. For radial flow turbine, you are going to see W over G, VW1, U1 plus or minus VW2, U2 over 1000 in kilowatt. Here, so in the radial flow turbine, you are going to see U1 and U2. U1 is the tangential velocity of vane at inlet for radial vane, and U2 is the tangential velocity of vane at outlet for radial vane. For sure, we'll talk more about what is the velocity of whirl, what is the tangential velocity when we go through the different types of turbines in detail. But this is one quick expression how to calculate the runner power. In this slide, we'll talk about the water power, WB. How to calculate WB or water power, a power supplied at inlet of a turbine, and also called water power. Water power is calculated by W times H over 1000 in kilowatts. What is W? As we mentioned, the weight of water striking the vanes of the turbine per second. And what is H? H is the net head on the turbine. Power supplied at the inlet of the turbine in SI units is known as the water power, is given by rho G Q H over 1000 in kilowatts, and rho is the density of water is 1000 kilogram per meter cube. So we can write WB in the form G Q H in kilowatts. Once you know the runner power, RP, and you know the water power, you can calculate the hydraulic efficiency. This is the first type. The second type of efficiency is called mechanical efficiency. Mechanical efficiency, the power delivered by water to the runner of the turbine is transmitted to the shaft of the turbine. Due to mechanical losses, the power available at the shaft of the turbine is less than the power delivered to the runner at the turbine. So the mechanical efficiency is the power at the shaft of the turbine divided by the power delivered by water to the turbine, or we call it SP, shaft power, divided by the runner power, RP. RP is already calculated in the previous slides, so now we need to calculate the shaft power. Once you know the shaft power, you can calculate the mechanical efficiency. So the third type of efficiency is called volumetric efficiency. Volumetric is the volume of water striking the runner of a turbine is slightly less than the volume of the water supplied to the turbine. Some of the volume of the water is discharged to the tail race without striking the runner of the turbine. So the eta V is the volume of water actually striking the runner divided by the volume of water supplied to the turbine. So if there is a waste water that will not strike the turbine, it will not contribute in generating electricity, so it will reduce the efficiency of the volumetric efficiency, eta V. So eta V will not become 100%, it will be reduced. The overall efficiency, so the overall efficiency, it is defined as the ratio of the power available at the shaft of the turbine to the power supplied by the water at the inlet of the turbine. So it's SP over WB. Once it is SP over WB, we can write it in terms like this: SP over WB times RB over RB. SP over RP times RB over WB. We mentioned that SP over RB this is eta M. SP over RP. And RB over WB, we talked about this before, is eta H. So the overall efficiency, it's a multiplication of the mechanical efficiency and hydraulic efficiency. So at the end, we can calculate eta naught, which is the power of the shaft over the water power in kilowatt, which is rho GQH over 1000. You can get the total efficiency or overall efficiency from this equation.